In this section, I'll cover instructions added to the instruction set for the MT-ASE. There are 8 instructions that have been added to the instruction set for MT. I'll go into each in detail. The fork instruction fires up a thread on a free TC. RS is a pointer to the instruction where the new thread will start executing. RT is the number of the current thread's general purpose register whose value will be copied to the new thread's general purpose register given in RD. This way, you can pass a value to the new thread by initializing one of its GPRs to a value with one of the current thread's GPRs. Some TC state is copied from the parent TC. The current or user mode state defined in the TC status TKSU field and what address space identifier defined in the TC status TASID field. Fork will only select the TC which is both free, defined in the TC status register A field being 0, and the TC is specifically marked as usable by a fork, identified by the TC status register DA field being set. If there are no TCs to allocate, a thread overflow exception happens and it is left to the OS to figure out what to do. A yield instruction allows a thread to control its execution. It can terminate itself, check for events to process, or wait for events to happen. When a TC issues a yield with RS as GPR 0, it will terminate itself. This could result in a thread underflow exception. This occurs when you're about to reach a situation where all the TCs that are available for a fork are stopped. The exception is used to tell the OS that it might stop forever, so it can decide what to do. When RS equals a -1, the thread may be stopped briefly while the yield indication is set out to the external scheduling policy manager. If this feature is supported by the policy manager, the manager may cause the thread to stop for a while, lower the thread's priority, or take other actions. The behavior is strictly a result of the implementation of the policy manager. Note that none of the policy managers supplied by MIPS use this feature. When RS equals a -2, the current value of all the yield qualifier signals are placed in the GPR number in RD. There is no scheduling effect. This is purely done to deliver the value to RD. When RS is greater than 0, the TC waits for one or more of the yield qualifier signals to be asserted and masked by a 1-bit in the GPR's value. The feature can be used to tie a specific thread to an external event. Several threads can be set up to wait on different events depending on the mask given in RS. As I have previously covered in the MT control register section, the YQ mask register enables a particular yield qualifier pin signals. So if the corresponding pin is not set, an invalid qualifier exception will be generated and the OS then can decide what to do with the thread. There are only 16 pin inputs, so only the lower 16 bits of the YQ mask register are used. The rest may float. After the yield instruction completes and the TC starts executing again, the GPR referenced by RD will contain the value of all active signals that are not masked by the YQ mask register. The yield instruction should never be put into a branch delay slot. Here are some advantages of using the yield instruction. The yield instruction with RS greater than 0 allows a thread to wait for an external event like an interrupt, only in a much more direct fashion. Since each thread has its own GP set, It's like using an interrupt with a shadow register set, but with the advantage of no vector fetch overhead. There are no cycles or cache states lost to saving and restoring a register context. This all adds up to no latency once the signal is asserted on the qualifier pin, no cycles lost to pipeline flushing and fetch redirection, because no execution is taken, versus 10 cycles of pipeline bubble on an interrupt. Post-yield instructions typically are already in the instruction buffer, so there is no additional fetch cycles. This method can be used to replace any interrupt, but it is particularly good to use in the place of an interrupt where the interrupt is very frequent and the interrupt service routine is very quick. The yield instruction can be used in user mode, so there is no need to switch to kernel mode to execute it. Interrupts do not have to be enabled. Say we have two threads in our system, thread A and thread B. Thread B starts an I/O call and use the yield instruction to wait for the I/O to complete. Thread A can use all the CPU cycles to execute instructions. Immediately when the I/O signal is raised on the qualifier pin, thread B begins to execute the rest of the driver. Once the device is serviced, the execution of thread B will continue, where it could just set up another I/O and yield again. Thread A and B continue to execute in whatever manner the scheduling policy dictates. I'm going to go into the move to and from a thread register instructions, which provide read and write access to another TC's general purpose registers. But first, let me tell you how to set up for these instructions. The VPE that the issuing thread belongs to must be the master virtual processor. This is done by writing a 1 to the MVP field of the VPE conf0 CP0 register. The target TC is identified by the value in the target TC field of the VPE control register. The target TC should be in a halted state, or otherwise unstable values might be written. Most of the time, these instructions are used to set up a TC before it is started or restarted, so this is usually not a problem. The processor must be in kernel mode, and access to coprocessor 0 must be enabled to execute this instructions. The MFTR, or move from thread register, will place the value of the register being read into the GPR referenced by RD in the instruction. This instruction can be used by an OS to save the context of a TC when a TC needs to be swapped out. Here is a corresponding move to thread register instruction. The same restrictions and setup that apply to the move from thread register apply to the move to thread register instruction. In summary of the move to or move from register instructions, they are used to move values to a thread or VPE registers other than the one executing the current code. All CPU registers can be accessed. The target thread is selected by setting the target TC field of the VPE control register. The VPE selected is the one the target thread belongs to. This VPE is set in the current VPE field of the thread's TC bind register. If you are trying to access VPE registers that are not in the current thread's VPE, the MVP field in the VPE conf register must be set before you can access the other VPE's registers. First, you need to set the target TC in the VPE control register. Then make sure that the current VPE field in the target's TC bind register is set to the other VPE. Then set the MVP field of the VPE comp0 register. Last, the target thread must be in a halted state. The disable multi-threading instruction will disable any other thread that is associated with the VPE the code is being executed in. It is a way to ensure that the current executing thread is the only thread executing in the VPE group. If you have another VPE with threads executing, they will still be active. The DMT instruction takes one register as output. This register will be written with the value of the VPE control register before the DMT took effect. When you want to enable the VPE to its previous state, you can use the EMT instruction to enable multi-threading, but if you are concerned with nested calls, it is more robust to replace the whole original value of the VPE control register. The EMT instruction will enable multi-threading for the VP you are executing on. The Disable Virtual Processing Elements instruction disables all multi-threading, including any other TCs affiliated with other VPEs, leaving the current thread running alone. The DVPE instruction takes one register as output. This register will contain the value of the VPE control register before the DVPE took effect. When you want to enable the CPU to its previous state, you can use the EVPE instruction to enable multi-threading on all VPEs. But if you are concerned with nested calls, it is more robust to replace the whole original value of the VPE control register. The Enable Virtual Processing Elements will enable virtual processing on the processor. In summary, the disable instructions force serial execution on a single VPE using the DMT instruction or across all VPEs on the processor using the DVPE instruction. This is handy for OS critical regions around the use of shared resources, such as global OS memory variables and shared CP0 resources like the VPE control register. They are safe and easy to use within exception handlers. Note, I will also cover later in another section inter-thread communications that can be used for semaphore control, which may be a better way to control shared resources. The DVPE and EVPE instructions are allowed only for privileged or master VPEs, so the MVP field must be set in the VPE conf register.